Yeah, so we are back in question 3. Now this one says, it says show that the general solution of this linear system on the interval of real numbers is this whole expression we're given here. So we want to show that the solution of this system is this. Now the first thing you're going to observe is that the system here is a homogeneous system. In other words, the f plus f of t that should have been here is 0. So it's a homogeneous system. Now, so we're told to show that by the time you solve this homogeneous system, you're going to get this solution vector. Now, how then do you go about that? So I'm going to explain to you by trying to encourage you to follow the whole things I'm going to do step by step. So I'm going to start by rewriting the system I'm given. So solution. So I'm giving x prime equals 0, 6, 0, 1, 0, 1, 1, 1, 0. That's what I'm giving times x. So I do not want to look at the solution here. So let's solve this normally. Now, the first step is normally a standard homogeneous system. A standard homogeneous system is written as this. So a standard linear homogeneous system is written as x prime equals ax. This is a standard linear homogeneous system. So the first thing I'm going to do in trying to solve this problem, so the first step, which I'm going to call step 1, is find a. Now by the time you compare this system here and this system here, you'd observe that this is going to be our A. Now the A is called the coefficient matrix. You can see it's the coefficient of x here. That's why it's called the coefficient matrix. So we're going to start by finding A. So we're knowing that this is A. So my A equals 0, 6, 0, 1, 0, 1, 1, 1, 1, 1, 0. That is the first step. Now the next step, which I'm going to call step 2, is to find the eigenvalues of A. So step 2, maybe I should write that in a different marker. Step 2, find the eigenvalues. Find the eigenvalues of A. That is, to find the eigenvalues of A simply implies that you should solve this equation here. So A minus lambda I equals 0. That's what you want to do. Find the eigenvalues of A. So that is, we want to solve A minus lambda I equals 0. So if we write our equation out, we have A minus lambda I equals 0. That is the same thing as, so A minus lambda I just simply implies you're deducting lambda from all the elements you have in the diagonal. And then what we're going to have is 0 minus lambda, that is minus lambda. You have 6, you have 0, you have 1, minus lambda, you have 1, 1, 1, and then 0 minus lambda, which is minus lambda. Then this equals 0. So we want to solve this equation here. Now by the time we find the determinant of this 3 square matrix here, what we would obtain is, so this implies that lambda cube minus 7 lambda minus 6 equals 0. And then at this point you want to punch your calculator to solve this cubic equation here. And then on punching our calculator to solve that, what we're going to have as a solution is lambda 1 equals negative 2, lambda 2 equals negative 1, and then lambda 3 equals 3. Now what you'd observe is that lambda 1, lambda 2, and lambda 3, they are not equal. So that implies that the eigenvalues, that is the eigenvalues, they are distinct. The eigenvalues are distinct. And then you recall, whenever the eigenvalues are distinct, then the solution because it depends on the kind of form we have in our eigenvalues. We have different cases, but for this case where the eigenvalues are distinct, the form of the solution, that's the general solution, should be of the form, say, x equals c1 k1 e to the power lambda 1t plus c2 k2 e to the power lambda 2t plus c3 k3 e to the power lambda 3t. Now, what you'd observe is that normally, assuming we're dealing with a normal homogeneous system that is not in vector form. Now, if I wrote this as my k1, so if you're going to neglect the k1 here, what we would have for the solution of a normal homogeneous system is going to be c1 e to the power lambda 1t plus c2 e to the power lambda 2t plus c3 e to the power lambda 3t. So we're going to exclude, we would have excluded k1, k2 and k3, but then the system we are solving now is in matrix form, so we have to include the eigenvector. That's just majorly the difference, a major difference that's going to help you in trying to probably memorize this formula, since it's not shown how it's been derived here, which I might show in another video. But for now, just know that whenever you have eigenvalues to be distinct, your x should take this form here. So where lambda 1 is the first eigenvalue and k1 is the corresponding eigenvector of lambda 1, lambda 2 is the second eigenvalue, k2 is the corresponding eigenvector of lambda 2, lambda 3 is the third eigenvalue, and k3 is the corresponding eigenvector of lambda 3. So what I'm going to go ahead is that I've already found the eigenvalue. Then the next step is to find the corresponding eigenvectors so I can have my general solution. So step 3, find the corresponding eigenvectors. So to find the corresponding eigenvectors is as good as saying solve a minus lambda I x equals 0. So this is exactly what this means. To find the corresponding eigenvectors, this is the eigenvector here. So we want to find x. So it just means just solve a minus lambda I x equals 0 for each of the lambdas that we have gotten. So I'm going to start by considering the first lambda here. Now for lambda 1 equals -2, then we have a minus lambda I times x equals 0 to give us, now a minus lambda, when lambda is -2, so we're going to replace, so in place of lambda I'm going to be putting 2 here, so you have -2, -2, -2. That's what we'll be having for that matrix there. So what we'll have there is going to be that's going to be 2 6 0 1 2 1 1 1 2 times x. So x, we said x is the same thing as x y z equals the 0 here is a column vector here. It's actually a vector 0 0 0. So we want to solve this, and then we recall from linear algebra that if you want to solve a linear system, what we first do is we row reduce this coefficient matrix there. Now row reducing this coefficient matrix, we obtain 1 0 3 0 1 -1 and then 0 0 0 times x y z equals 0 0 0. So this is what we obtain. So let me write this whole thing here in equation form. So we're going to have 1 times x, that is x, plus 3z equals 0, and then 1 times y, that is y minus z equals 0. Now to solve this thing, the first thing you need to look, or you need to take into consideration, is which of them is a free variable. So we'd observe that z is the free variable there. So the free variable here, free variable is z. Now since z is a free variable, it simply implies that z is the variable which I could just give any number. I could give it any number. It's a free variable, so it could take any number. So I'm going to start by setting, I would say let's set z to, let's say 1. Now when z equals 1, when we come back to this equation, y equals z, bringing z to the other side, so and that is equal to 1. So now we have y equals 1, and then coming here we have x equals negative 3z, and that's going to be negative 3 times 1, which is negative 3. So I have my x equals negative 3. So I've gotten my first eigenvector to be k1 to be equal to x, which is negative 3, y, which is 1, and z, which is 1.